All right, so today we're talking about logarithmic functions. Well, the logarithmic functions is the inverse of the exponential function. That's why we start with exponential function, because it's the inverse of the logarithmic function. So, as a reminder of log functions, I'm sorry, inverse, how do we find inverse? Switch to x and y. If anybody was confused about that, that's why I wrote it in the notes. All right, so again, I put the exponential function here as a reminder of what we learned when we did exponential function. Do you guys want some time to write down the critical things there? It's okay, I'm boiling water anyways. Apparently it works. Just loud. No, tea. Apparently I have something called a cold stomach. That's when a stomach that gets irritated when you put cold stuff in it. That could affect it as well, yes. Wow, that thing is loud. Sounded like my hot shot too. My hot shot was the same way.
And you wonder why I don't come to class. I'm just kidding.
I know why you don't come to class. I know you would come to class if you could come to class. Okay. Oh, let me give you guys, keep on giving you guys some time. You guys want to, some of you guys can copy and paste. Yeah, yeah. You can just select that graph and all the domain and range and just copy and paste it. You can start it because it's just switching to x and y, right? So take everything that we have over there on the left and switch to x and y, and then plot it. And you'll be like, done. Good news is that we're almost to landing. Like playing with it, huh? Is that still good notes? How are you liking it? Yeah, I don't like to use any of the tapping stuff. I just select what I need. We have tapping. I don't know if it's under handwriting. No, themes, document, typing, auto, gestures. Like you got 2-finger tap, 3-finger. No, I think it's you're tapping the. Gesundheit.
Wait, I just realized what you said.
Hopefully you didn't twist my words. Are we all ready? All right, so here's my question. When we graphed, or I should say, when we came up with the equation of a graph of a exponential function, what did we identify first? We identify the horizontal asymptote. Okay, let's take the inverse of that. What would that become? No. So we first identified the horizontal asymptote, right? Which is y equals 0. What would it become if I took the inverse of that? It'd be x equals 0, which is that still a horizontal asymptote? What is that now? Oh, now it became a vertical asymptote. So now it became a vertical asymptote at x equals 0. Right? Because we switched to x and y. Does that make sense? And then we identified what? What was the second thing we did with graphing? I mean, identifying the equation of a graph. What was the second thing we did? This is going to be critical because we're going to also graph a logarithmic. What was the second thing we did? So first we identified the asymptote. The second thing we did was identify the critical point, which was 1 unit away, right? So if we look at these critical points here, let's switch to x and y. What does 0, 1 become? 1, 0. Okay. So now it becomes 1, 0, which is here, right? Negative 1, comma 1 over b would become 1 over b, comma negative 1. And 1, comma b would now become b, comma 1. Hello? So now I have a graph like this. Oh, let me do it this way. You guys see how all those x's and y switched? Right? What happens to my domain and range? They also switch, right? The domain becomes the range becomes the domain. What is the equation of this graph then? This logarithmic function? Switch to x and y. So it is x is equal to b raised to the y power. Like literally, I just want you to switch to x and y's, right? That's all we did. Switch to x and y's. Ta-da, we switch to x and y's. Is there anything we forgot? We're good, right? Okay. So, notice the difference here. If the graph crosses the y-axis, that means I must have an exponential function, right? So no matter if I flip over the y-axis, still crosses the y-axis. Flip over the x-axis, still crosses the y-axis. I have an exponential function. Logarithmic function crosses the x-axis. If I flip over the y-axis, still crosses the x-axis, right? If I flip over the x-axis, still going to cross the x-axis. So that's how I'm going to determine if I have a log function or an exponential function, right? So this way I know what to put in, okay? Now, here's the problem, though. When you look at this equation, you're thinking that there should be a log in there somewhere when it's a logarithmic function. Yes? Yes, okay? Thinking in your head is allowable. All right? Please feel free to do so. When you stop thinking, then we're in trouble. Okay? So in the log form, there's actually, so this is the problem with logarithmic functions. There's two forms. This is one form. We call this the exponent form. And then there is the log form. Now, we do have to be able to go back and forth between the log form, exponent form, back to log form. We have to be able to do that. But before I talk about that, let's talk about the log form. What is this saying? Because a lot of times people think that log is something. If you just write log, it just means what you dropped in the toilet this morning, or what you put in your fireplace to burn. Those are called logs, right? That's about it. So if you just write log, it means absolutely nothing unless you take the log of something. In fact, if you type log in your calculator, it's going to start parentheses because you got to take the log of something. Same thing here. If I said square root, you're going to ask me square root of what? People don't just write down square root. If you just write log, it's the same thing as saying square root. You're like, okay, and? Right? So same thing. If you tell me log, I'll be like, log of what? Right? So I would ask you the same thing. So, and the base is kind of like the index. The square root versus the cube root. How the index changes, right? This is known to be a 2 when there's no number there, but this is an index of 3, right? The base is kind of like that. Is that fair? Okay. So when I say log base b of x, it's kind of like saying I'm taking the bth root of something. Okay. So let's take a look at if we have something in log form. How we would convert that to exponent form. Now, before I do anything, I'm going to say this. Everybody look up here. No matter which form I'm looking at, over here on the right, this b, we call it a base. This b is also called a base. Understand? So no matter which form I use, that b is a base. On the left is a base raised to a power. On the right is the base of a log. Okay? So this is how I typically do it. You guys can do it however you guys want to, but this is how I look at it. Here it goes. So everything is based on the base, right? So this base goes, you know, log, you treated me like a log all these years. I don't enjoy it, so I got a job on the other side. I'm going to be their base. So since there's the base, so that means, again, it'd be base raising to a power. This log, this boss, goes, I've been treating them like a log all these years. I'm so sorry. He gets so depressed that he disappears. And now that is my exponent form. The reason why I put an exponent form, because I can solve this x for x. What's x equal to? 1 over 2. Oh, what? Okay, so what do I do to 36 to get 6? I take the square root. So the question is, what is that power if I'm taking the square root? So this is the reason why, in the past, I drew this picture here. Right? I said that the grass is the separator of light and dark. And I said, if you don't believe that under the grass is dark, ask someone that was buried 6 feet under. If it was dark down there, they're going to probably tell you yes, if they can answer you, that is. But what grows underneath is roots. And the sun gives us power. So this is the fraction I want you guys to think about. Right? That is the power that we got to talk about. So whenever I talk about the square root of 36, right? Number one, I know that the root is a 2. Is that right? Because we're talking about square root. And the power on the 36 is 36 raised to the first power. Yes? So that means this is going to be 36 raised to the Thank you for saying something. I got you. Is everybody else okay here? So it's y is equal to log base 3. Questions? Are we okay? Not bad, right? But notice that how I identify the equation for the exponential function or exponential graph versus the log graph, it was the same. I identified the asymptote, what's 1 unit away, how did I move from one critical point of the parent function to this critical point, wrote the equation, solve for b. Right? So no questions. We're good. All right. So here's the problem. On your calculator, you see two different log functions. You see log, and you see ln. These two, one is called the common log, and one is called the natural log. So let's talk about these two first, and then talk about what we've been writing. Okay? So what you see on your calculator is log of x. Okay? It's just log. Well, when it's just log, this is called a common log. The base of this common log, is actually a 10. So when there's no number written there, is assumed to be a 10. So when you hit the log there, is a log base 10. Got it? Okay? Is a log base 10. Just like the square root, the 2 is not written in an index, but because there's no number there, we assume it to be 2, or we understand it to be a 2. Same thing here. There's no number there on the base for the log. We understand it to be 10. The other one that you see on your calculator is y equals ln of x. This is called a natural log. The reason why it's called a natural log is because the base is that e that we had in the last class. The e is a natural number, hence the natural log, 2.71 blah, 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 blah. So whenever you see ln, then we're talking about a base of e, which is the natural log. But what we've been talking about is this. No special name here. We just know the base is base of b. Are we okay so far? The problem is that with a regular calculator, you don't have log base b anywhere. Sad calculators. Maybe. Now, we said that there's a critical point here, right? 1, 0. Is that right? What does that even mean? but it's a point. Okay, so let's rewind. So remember how we said that with exponential function, we always have 0, 1. How do we know we always have 0, 1? It has nothing to do with asymptote. Before we even talked about asymptote, we already agreed it's always going to have 0, 1. Now let's look at back here. The parent function, but any base raised to the 0 power is always going to equal to what? 1. So if I plug in the x value as 0, didn't matter the base, my y value equal to 1. Hence, 0, 1. Right? 0 is the x value. 1 is the y value. Right? Didn't matter the base. So fast forward to today. What does it mean by 1, 0 then? Wait a minute, why are we saying raised when there's nothing being raised here? When have we ever said when y equals this, x equals this? Wouldn't it be the other way? Thank you. So we're saying this. Oops. I did boo-boo. We said that if we take the log of 1, it'd be 0. If we take the natural log of 1, we get 0. And we take the log base b of 1, it equals 0. Right? Because that's the x comma y. It doesn't matter what the base is. I still get the log of 1 equals 0. Don't believe me? Take the log of 1 and tell me if it equals 0. Take the ln of 1, see if it equals 0. Yup. We okay there? Just do this, Chan. If I take the log of 10, that's going to equal to 1. What should your question to me be? Why 10? Why do you choose 10? Oh, because that's the common log, and the common log has a base of 10. Holy crap. So in other words, if this number in here matches the base, it goes away. And I'm left with just 1. Wouldn't that mean that it's the opposite operation? So are you saying that if the bases are the same, they cancel each other out? So all I got left is P. P. Not PP, but P became P. Yeah, go ahead.
On MLM, it was this lecture. It was like 3, 3 to the 5th, you know what I mean? And it was 5 for the answer.
Mm-hmm.
So is that what that is?
Mm-hmm.
That was my question.
Because they are opposite operations, but as long as the bases are the same. Just kind of like square and square root, cube and cube root. If the index and the power are the same, they cancel each other out. Make sense? So this is the same thing. As long as the bases are the same, bye-bye. So the ln of what would give me 1? ln of what would give me 1? It'd be e, because that is the base. The base is e. So if I did ln, ln of e raised to the p power, I'll get p. Because the bases are the same. They cancel each other out. Okay. Log base b of what gives me 1? B. Does that make sense? Question is, what does that look like the other way around? And you're probably wondering what I mean even by that. So if I said the cube root of x to the third, right? You said that would equal to x. Is that true? Right? But what does the other way around really look like? It would mean this. Right? If I took the cube root of x and cube it, it will also equal to x. Make sense? So that's what I'm trying to find. What's the other way around of this? Because I know that, but which is I know this, so I need to find what this would be for this. Okay? All right. So here it is. Remember how we said that the base has to be the same. Is that right? Yes? So this is what this means. Ten raised to that power. If the bases are the same, they're opposite operations, so the p will be left. So what would this be? Very good. And what would this be? Raised to the power of? Yeah. Oops. Got to put the base in there, right? Log base b of p. So guys, when you look at this, I want you to understand something. You see it as 12 different rules. But really, it's only 4 different rules. In fact, really only 3 different rules. Because the second and the third are the same thing. Mean the same thing. So really, out of all of this, you only have 3 rules. Does that make sense? It's just written differently based on its base. Right? So I don't want you to think, oh my goodness, I got 12 things to remember. It's not. It really is only 3 things. All okay there? So here's the thing. Remember how I taught you guys how to do this right here? You guys remember that? So how would I utilize what I just learned with this? So if you didn't want to learn about the base being moved, okay, then here's what I would tell you to do. So when I have this right here, I identify the base. The base is 36. What's the opposite operation of a base of 36? log base of 36. Well, if I do that to one side, guess what I have to do? I got to do it to the other side. So the left side is only going to be x left equals 2. Wait a minute, that looks familiar, doesn't it? Looks like this, huh? Everybody see that? So I can just use math to do it. So on the right, I want to convert it back to this thing here. Okay, I identify the base, 36, right? The log is already there. So what's the opposite operation of that? It'd be 36 raised to this power. Here, let me shrink that a little bit so it looks like it's to the power. Oops. Right? If I do it on the right side, guess what? I got to do it to the left side. What's left on the right side? Voila. So again, I can use the properties that we just used to go from log form to exponent form and exponent form to log form. Are we okay there? Questions there? We're good? Let's talk about the properties of logarithms. Sorry, I shouldn't say equals. So we got to be able to go back and forth. It's going from left to right or right to left. Which direction would be considered condensing? Which direction would we consider expanding? Going from left to right would be considered expanding. Going from right to left would be considered condensing. Right? If you went and picked up a bunch of logs and threw it in a paper bag into one large pile of logs, that'd be condensing. Multiple logs into one bag of log. When we put it in a neighbor's porch and light it on fire and ring the doorbell, and they come out seeing that things are on fire, they step on it, guess what? That one pile of log gets expanded into multiple pieces of log everywhere. So there's multiple logs everywhere, that hence it expanded. Right? So from a single log to multiple logs, expand. Multiple logs to a single log, condense. So these rules are made really for expanding or condensing. Just so you understand, all three rules will be used. Got it? However, it's not 3 steps. Like PEMDAS is not 6 steps. It's actually 4. Right? So in these properties, product and quotient rule will be used as part A, part B of one step. And then the power rule. Or the power rule will be used, and then the next step will be product quotient rule as part A, part B. Does that make sense? So it is these two, then this, or this, then these two. That all depends on expanding versus condensing. Any questions there? Nothing? Okay. Do you guys think I need to expand or condense? Did I just expand your keychain or condense it? Why? Because it went from one keychain to everywhere. Did I expand or condense? Because it went from multiple keychains to one. How many logs do I have? So that means I have to. If I have one, that means I would go like that. I will expand. If I have multiple, that means I want to condense them. So if I only have one, that means I want to expand. If I have multiple of them, then I want to condense. That's why I know that I have to expand here, because I only have one log. Okay? Is that fair? I figured that example would make more sense to you, to all of you. Okay. What is the first operation you see? And just so you guys know, when I say operation, I mean add, subtract, multiply, divide, not square root. Okay? So division, yes? Hence the quotient rule. Yes? Okay. Does that make sense? What's the next operation you see? Huh? Well, we got that subtraction because of the quotient rule, right? Remember, we have to use all three rules. So we gotta look for the product, which is right here. Everybody see that? Isn't that 25 times y to the third? That's the product rule. What's your question going to be? Is it what am I going to do now, or is there a different question? Yeah. Why is there extra set of parentheses there? What is that for? What's that green set of parentheses? Where did it come from? Because there was no parentheses up here. Why is there a parentheses here? Great question. So finish copying what you copy, and then I'll talk about that. Thank you for being so polite. So if you look inside the parentheses there, right, you have a single number on top divided by a product of the two numbers on the bottom, right? How would you do that problem? Would you multiply the 2 times 5 first? Yeah. So you would do that first. Better yet, let's do it this way. If you were to plug this in your calculator as 3 divided by 2 times 5, you'll be wrong. Because this does not equal 2. That would be that. See what I'm talking about? That's the reason why the parentheses is there. Because it's the top divided by the product of the bottom. That's why the parentheses is there. Okie doke? So I did the quotient rule, the product rule, now I got to do the? That means I'm going to try to make everything have a power. Okay? So. Well, the y is pretty simple. That already has a power of 3. That's great. So let's talk about this one here. Square root x is x to what power? Huh? 1/2 power. Now we got to figure out this right here. Okay. So to pick, so 25 doesn't have a lot of bases, right? 25 is just 5 squared. That's all we got, right? Okay. So let's say 64. 64 is 2 to the 6, 4 to the 3rd, or 8 squared, right? So there's 3 different bases there that I could use. And you're going to be wondering, which base do I use? So the base should be determined on the base that's already given. So if you look at my base, it's a base of 5. Luckily for me, 25 has a base of 5. 5 what? 5 squared. It's 25, right? So that's how I would choose my base. Now, if this number was, let's say, 23, and I can't make it to a base of 5, then I'm just going to leave it as log base 5 of 23. But if I can make it to that base, then I will. So this is now going to be 5 squared. Does that make sense? Do we understand what the heck just happened? Is your question where the log base 5 of 5 went? What do we know if the bases are the same? And left with? So we're wondering about this, yes? Here, let me do it this way. So does that look like this right here? And what does that equal to? 1. See it? And 2 times 1 is just 2. Oopsies. Hopefully we catch this one as well. Did we catch that one? Just drew me that negative through. Here's the ultimate question. Can we go from here back to this? But you can. because the steps are already given to you in this direction, the steps are also given to you in this direction. So I would recommend to you that at some point that you think about this, going to here, then 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 going to here, which we call condensing. And notice what will happen. You're going to go with here, and then you're going to deal with the power rule first. And then you're going to do product and then the quotient rule as part A, part B. Okay? Notice that because there's no log in here, that you have to replace it with log base 5 of 5, because that's equal to 1. Now, here's the other part. Whenever I see this problem right here, guys, I see minus, minus. When I see minus, minus, I think divide, divide. So have you ever done 3 divided by 2 divided by 5? No. It's weird. You don't go 3 over 2 over 5. That's weird, because you don't know which one has to divide first, right? So whenever I see minus, minus, or divide, divide, I have to think about grouping these two and pulling negative out of those two. Does that make sense? Hence, that's why this will happen. If it's a minus plus, no big deal, right? Plus minus shouldn't be a big deal either. It's that minus minus that kind of gives me the heebie-jeebies, because it's divide divide, which we don't usually know, right? Last but not least, the reason why we have change of base is because when these lessons were taught, we only had these calculators, which we only had the common log and the natural log, right? So the problem is that we couldn't figure out how to find log base 12 of 15. You too, Shia, right? So there's no way of plugging this into the calculator. So we have to use something called a change of base. So the change of base states that log base A of m is either equal to the log of m divided by the log of A, or the ln of m over the ln of A. So you can use common log or natural log. They both will work. Both of those will give you the same answer. So if I was to apply this over to the example here on the left, I can say this is equal to log of 15 divided by the log of 12. Or the ln of 15 divided by the ln of 12. Either way, this, if you put it in, is approximately 1.0898 ... The problem with this is that you have to read the direction. The direction might either ask for an exact answer or an approximate answer. Approximate answer would be the decimal form. This would be approximate, because you're not going to write all the digits out. This right here above it is your exact form. Okay? So if it asks for exact form, that's what you have to do. So even if you can type in log base 12 of 15, you still need to know this rule, because you need to know how to get the exact value. So in exact value, you have to either have log or natural log in your answer. Is that fair? Any questions there? Nothing? Awasa? Okie dokie. Ladies and gentlemen, please have a wonderful, blessed weekend. Please be safe. Love you guys. See you guys next week. Later.